I'll give you just a couple of examples from biology of oxidation of organic molecules. Generally, when we talk about oxidation of organic molecules, what we're talking about is adding hydrogen and removing oxygen. And this process shown here is cellular respiration, which is the process basically where the cell releases energy so that it can do everything it needs to do. So glucose is the most common fuel in the cell. Like the cell can use fats and other things, but glucose is kind of the primary fuel. And in glycolysis, glucose is broken down into pyruvate, which is then further broken down into carbon dioxide. So if you look at this process, this is an oxidation process. So basically, if you look at the ratio of carbon to hydrogen to oxygen in glucose, it's 1 to 2 to 1. Then in pyruvate, carbon to hydrogen to oxygen, it's a 1 to 1 to 1 ratio. So in other words, it's oxidized. It's got more oxygen and less hydrogen. And then when we go to CO2, we have no hydrogen at all, and it's a 1 carbon to 2 oxygens. And in the same process, I don't show it here, but we also form water. So this is a favorable reaction because both water and carbon dioxide have a more favorable distribution of electrons than glucose does. So this is why glucose is such a good fuel and why we can eat it and get energy from it. And in this reaction, oxygen is the oxidizing agent. So now let's look at reduction of organic molecules, one process of reduction. There's many others, but this is probably the most classical example, photosynthesis. The photosynthesis is a process in which plants take carbon dioxide, the molecule on the right, and then they convert it into glucose. So in this process, we do the opposite of oxidation. We have basically CO2, so there's no hydrogens in that molecule, and we keep adding hydrogens until we end up with C6H12O6. So this reaction requires energy, which is why plants require sunlight to grow. Another reaction we're going to talk about, combustion, is one that we've already discussed a lot this semester. This is a reaction in which an organic molecule reacts with oxygen to form carbon dioxide and water. Now, combustion is actually a type of redox reaction, and two examples are shown here. So this is burning of methane and burning of ethanol. In each case, we have an organic molecule and oxygen as reactants, and we have carbon dioxide and water as the products. Combustion reactions always release a lot of energy, and that's because the electrons are essentially going towards the more electronegative oxygen atom, where they can be closer to the nucleus, the positively charged nucleus, which is more energetically favorable. And this is why organic fuels such as methane and octane are such good fuels because basically when they react, the electrons end up in a more favorable configuration. I should also mention that oxidation of sugar or respiration is a combustion reaction. So if you look at the combustion of sugar here, we've got glucose plus oxygen producing carbon dioxide and water. So this releases a lot of energy, but our cells are very clever and are able to harness this energy. So instead of producing a lot of heat, which would kill the cells instead turn this into other forms of chemical energy that the cell can use to do what it needs to do. The remaining reactions that I'm going to discuss are a little bit, they're fairly self-explanatory. For example, gas evolution is a reaction in which a gas is formed. So when, for example, when hydrogen sulfate and lithium sulfide react. So these are both in aqueous solution, so in water solution, but the product that they form, hydrogen sulfide, is a gas. And then there's also another product, lithium sulfate. So lithium sulfate is aqueous, but if we have at least one gas formed, it's considered a gas evolution reaction. You can tell that gas evolution is taking place because you can see bubbling in aqueous solution. Another type of reaction is single displacement, and this is one in which one element displaces another in a compound. So, for example, in this single displacement reaction, we have copper chloride, and the zinc then displaces the chlorine to make zinc chloride and then solid copper. We also have double displacement reactions, and these are reactions in which atoms swap places in two different compounds. For example, if we have AgNO3 and NaCl, so that's silver nitrate and sodium chloride, the silver and the sodium can swap places, so we end up with AgCl and NaNO3, or sodium nitrate. Now the AgCl, or silver chloride, is a solid, so it precipitates out of solution. So note that this is a double displacement reaction, but it's also a precipitation reaction. So reactions can belong in more than one category depending on what is happening. I just have two different more types of reactions to talk about. First is synthesis. So in a synthesis reaction, two chemicals combine to form one. So for example, if we react sodium and chlorine to form sodium chloride, we started out with two different elements, and we end up with a single compound. So this is a synthesis reaction. And we also have decomposition reactions, which are essentially the opposite. This is when one chemical breaks down into two substances. So, for example, if we have water broken down into hydrogen gas and oxygen gas, we start with one and end up in two. This is a composition reaction.